Nuclear Energy, Key to Tomorrow. Produced by WQED for the Educational Television and Radio Center. In cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, atomic fuels. Your host, Dr. Warren Witzik, Manager of Reactor Physics, Bettis Atomic Power Division.
Hello. Welcome to another discussion in the series on nuclear energy, the key to tomorrow. In this discussion, we're going to talk about atomic fuels. You're familiar with the kind of fuels that we use in a chemical reactor. They are coal, oil, and gas. In this discussion, we'd like to talk about the fuels that we use in a nuclear reactor. In our series of discussions on matter, we talked about the periodic chart of the elements, and we built up the atoms starting with hydrogen and going to the very heavy ones down in here with the uranium. Now, for the atomic fuels, we find them located at the heavy end of the table, and the chemical fuels tend to be up at the lighter end of the table. For example, in coal and oil and gas, we find predominantly hydrogen and carbon. We burn these fuels, producing energy and a waste product, an ash. In a similar fashion, we can burn our atomic fuels: uranium, thorium, and plutonium. Supposing we catalog these things at the board. We start out for our fuel with the most familiar one, uranium. And then the one that we mentioned next was thorium. And then plutonium, this one being the man-made one. Now, in order for us to utilize these fuels, we need some magic metals, as I like to call them. Magic metals. Now, really, they're not so magic, but rather we should say they're very new. An example of one is zirconium. Zirconium was only a laboratory curiosity just a short time ago. A second one is beryllium. A third one is hafnium. Hafnium is extremely useful as a neutron eating material. Now, there are other materials that I could mention, but that would be a source of a whole discussion. There are rather common materials in use today, such as lead and tungsten. Oh, come in. Hello, Ben. Good to see you again, Ben. This is Dr. Benjamin Lussman of the Westinghouse Electric Corporation, and Ben has consented to talk with us in greater detail about these atomic fuels and about these magic metals. Now, Ben, we're interested in these atomic fuels both today and tomorrow. How do you see them being used today?
Well, these atomic fuels are used in nuclear reactors, such as the pressurized water plant at Shippingport, Pennsylvania, where electricity is generated and is fed into the transmission lines of a public utility. Similarly, these fuels are also used in mobile power plants to propel atomic submarines, merchant vessels, rockets, and so on.
So today, then, you'd say we were limited to the production of electrical power and propulsion. Now, what of tomorrow?
Well, there has been much speculation about the use of nuclear power plants in private automobiles, flying machines, scooters even. However, I think today we have to visualize the role of these atomic fuels primarily as replacements for our conventional fuels, coal and oil, as they become depleted.
Then we're going to embark in further details on these now. How have you decided to best explore these fuels with us?
Well, let's go into the laboratory,
Fine.
Warren, where we have a number of displays set up. Uranium is quite a common element in the Earth's crust and is quite widely distributed. In fact, there is sufficient uranium in ordinary granite that if it could be economically separated, as much energy would be produced from granite as from an equal weight of coal. This chart shows the distribution of economically workable deposits of uranium over the Earth's crust. As you can see, there are large workable deposits in northern Canada, considerable deposits in western United States in the Colorado Plateau. Much of the uranium which is used in the world today comes from the Belgian Congo. Very rich deposits are present in Czechoslovakia. India has quite large deposits of thorium, and large deposits are present elsewhere in the world. Here we have on the desk some typical ores in which uranium is found. Now, I will, as you know, you've heard of prospecting for uranium ores using Geiger counters. And here the use is made of the natural radioactivity of these ores in order to indicate their presence. And we will show by the clicking noises made as we bring the counter in contact with each of these various minerals, the presence of radioactive uranium. Now here, for example, is a sample of pegmatite ore containing uranium. And you can tell from the clicking sounds the presence of uranium in this mineral. The ores of the Colorado Plateau consist primarily of carnotite, as indicated here. And this is another form of carnotite. Another type of ore containing uranium is pitchblende. This is the type of ore which is found in Czechoslovakia. And you can tell here again from the clicking of the counter the presence of considerable quantities of uranium. The mining of uranium is performed in quite conventional manner. This is a photograph of a typical location of a mine in the Colorado Plateau. The ore is mined from this by more or less conventional techniques. It occurs in deposits, in loads. It is pneumatically mined from these loads, shipped in these small carts, and then sent by truck or otherwise to plants where the ore is crushed, graded, concentrated, and classified. These concentrates are then shipped to refining plants where the pure form of the material is separated. And this is a typical form of one of the uranium salts. And here again, you can tell from the clicking of the Geiger counter that this material contains a high uranium content. If you could see the color of this, it is a very brightly colored, very colorful salt, a bright orange in color. This these salts of uranium are converted to the form of uranium tetrafluoride, which are then reacted with calcium or magnesium metal and reduced to form metallic uranium. Metallic uranium is melted in vacuum, cast into ingots, and then rolled down by more or less conventional metallurgical techniques to produce rods or other forms similar to those shown in the bottle. Now, we've talked about uranium. Thorium is similarly mined, refined, and reduced to metallic form. And thorium metal is, again, a silvery metallic material very similar to uranium. It is much lighter than uranium, which, of course, is a very heavy metal. The final fuel, which Warren talked about, we can represent by this bottle.
Ben, you've got an empty bottle there. What are you trying to tell us with this empty bottle?
Well, Warren, plutonium, as you know, is a highly toxic material. We would not like to carry it around in bottles. It is also quite a scarce material and has to be man-made.
Supposing I explain how we make that element, plutonium, Ben. We start out with uranium-238. We take this isotope of uranium, we put it in a nuclear reactor, and bombard it with neutrons. This makes it uranium-239, which almost instantly decays with the emission of a beta particle to neptunium-239. It more slowly decays with the emission of a beta particle, becoming plutonium-239. The plutonium is chemically different than the uranium. So when we put the uranium in a reactor and irradiate it, we can extract the plutonium by a chemical change, you see. It's different chemically, and so we can extract it. Thorium, as we obtain it originally, is not fissionable readily. We put it in a reactor. We add neutrons to it in the same way as we did with our uranium to make plutonium. We add neutrons to it through a process which allows radioactive decay, and it then comes to uranium-233. So here again, we have created from a non-fissionable material a fissionable material. And it is chemically different than the thorium. And we use this chemical difference to separate it after it's been created within the reactor.
Well, in addition to these fuels, you've all heard about the isotope of uranium, uranium-235. Now, uranium-235 occurs in amounts less than 1% in all natural uranium, the bulk of natural uranium consisting of the isotope uranium-238. Now, as distinguished from the fuels which Warren told you about, the separation of uranium-235 from U-238, because of the chemical identity of these two isotopes, cannot be performed by chemical methods, but has to be performed by physical methods depending upon the difference in weight between 238 and 235, 238 being, of course, much heavier than uranium-235. And we've shown schematically here that the uranium is converted to a volatile salt, uranium fluoride. The natural uranium is then separated by physical methods to uranium-238 and 235. This process is performed at the plants at Oak Ridge, Tennessee. And it is this isotope of uranium, uranium-230, and which is the fissionable material which is used in the power plant for the Nautilus submarine.
Well, now, Ben, we've sort of discussed how we get these atomic fuels, and in our introduction we discussed the magic metals. Supposing we talk a little more how these atomic fuels require the use of, or how do we use the magic metals in conjunction with them?
Well, the particular fuel which is used and the magic metal which is used in conjunction with that fuel depends entirely on the type of reactor which is used, and most specifically on the type of coolant which is used in this reactor. Now, here we have shown on the board a schematic model of a typical reactor. And let us take, for an example, a reactor which is cooled by the use of pressurized water, water at high temperatures. And you see the pressurized water enters the reactor, circulates around the fuel, where heat is being produced and then carries this heat from an outlet of the reactor vessel to a steam generator where useful steam is produced. Now, any of the fuels that Warren mentioned, uranium, thorium, plutonium, can be used as a fissionable material within such a reactor. However, each of these fuels react chemically rather violently at high temperatures with the hot water, and therefore it is necessary to surround the fuel material with a cladding or structural material. And here is where the magic metals which Warren mentioned comes in, because, for example, in pressurized water reactors, we can use as cladding materials such as zirconium, or the more common materials, aluminum and stainless steel. And the particular structural or cladding material used with the particular fuel illustrates one of the complexities of reactor technology. For example, if stainless steel is used as the structural material in a nuclear reactor, then the problems of the reactor engineer and the materials engineer are relatively easy. However, because of the high neutron absorption properties of stainless steel, it is difficult for the physicist to make a good reactor out of such a structural material. If aluminum, on the other hand, is used as the cladding material in a reactor, the problems of the materials engineer are relatively simple, because aluminum is a material whose technology has been quite well worked out. The problems of the physicist also are relatively simple, because aluminum has a low capacity for the absorption of neutrons. However, since aluminum reacts quite violently with water at high temperatures, or relatively rapidly with water at elevated temperatures, and since its strength at elevated temperatures is somewhat limited, the problems of reactor engineers in producing thermally efficient systems become much more severe. If zirconium is used as the structural material in a pressurized water reactor, then the problems of the physicist are eased, because zirconium has a low neutron absorption capacity. The problems of the reactor engineer are simplified, because zirconium has good corrosion resistance, good strength at elevated temperatures, and therefore higher temperature water can be used in the reactor. However, since zirconium is a material which is new in materials technology, it cannot, the problems of its use are much more severe.
Ben, since we understand now why we need these magic metals, let's treat them as we did the atomic fuels and discuss their origin and down through the processing.
Up until 8 years ago, zirconium found its principal application in such small-scale uses as getters in vacuum tubes, techniques for producing high vacua inside of vacuum tubes, and in fact small quantities of zirconium are still used in such an application today. However, the problem facing materials engineers was application of zirconium from these gram lots for such special application to tonnage lots which are required in a nuclear reactor. Now, zirconium is a relatively common material. In fact, entire beaches in Oregon are made up of a mineral of zirconium, zircon sands, and this is an example of the type of raw material containing zirconium. This zircon is converted to other forms, zirconium carbide, which is then and zirconium chloride, which is then reacted with molten magnesium to form a product known as sponge zirconium. It's called sponge zirconium because, as you can see, the metal produced has a rather spongy structure. Now, this material can be further refined to form by the iodide process to form what is known as crystal bar zirconium, and this is an example of the rather handsome product produced as a result of this refining process. And in fact, it is this material, crystal bar zirconium, which was used as the structural material in the prototype of the first submarine reactor core, the Nautilus core. However, we have learned today how to use the less pure and therefore less expensive material, zirconium sponge. Now, this material is melted in arc furnaces to form ingots of zirconium, and this is an example of a small ingot produced by the arc melting process. We are, of course, today producing zirconium in the form of ingots weighing many tons and up to 12 or 18 inches in diameter. Material in ingot form is then further worked on to useful shapes. And here are some examples of some shapes in which zirconium is used in reactors. Here the zirconium has been worked on in the form of a tube. And here is the tube is cut away, and you can see the uranium in the form of pellets of the oxide of uranium. Uranium oxide are stacked inside the tube. This structure is known as a fuel element. And this is the type of fuel element which is used in the pressurized water reactor plant at Shippingport, Pennsylvania. Now, another form of fuel element is in which zirconium is used is a plate type of fuel element. And this is a typical example of a plate fuel element in which the enriched uranium isotope that we mentioned previously, uranium-235, is sandwiched between two plates of zirconium, and the three components rolled out to form a structure such as this. And this plate type of fuel element is another one of the fuel elements which is used in the Shippingport plant.
Ben, I like to call one of the other magic metals, hafnium, a sister metal of zirconium because it is so much like zirconium. So how does it occur, and what do we know about it?
Hafnium is a common impurity in all zirconium ores. For example, in these particular beach sands, hafnium occurs to about 2.5% by weight as an impurity. Since hafnium has a high capacity to absorb neutrons as compared with the relatively lower capacity to absorb neutrons of zirconium, it is necessary to separate the hafnium from the zirconium in order to properly utilize it as a structural material. However, the hafnium, which is separated from the zirconium, can be used in the form of what is known as control rods, which are inserted in the nuclear reactor to control the progress of the nuclear reaction.
Ben, in one of our previous discussions, we've gone into the fission process in some detail, and we have described how uranium, when it fissions, goes into various fragments. I wonder if you could tell us a little about how these fission fragments affect this whole process of atomic fuels.
Well, just as in the burning of carbonaceous fuels, waste products are produced. And here, for example, we will ignite a piece of paper, and you can see that copious smokes, gases, and whatnot are produced during the combustion of this form of fuel, this carbonaceous material, as well as solid fission products, or solid waste products here. Similarly, now, in the nuclear burning of uranium, waste products, as you mentioned, are produced. Now, we cannot talk of burning of uranium in the same sense that we talk of burning of carbonaceous materials, since in the latter case this is a chemical process. In this case, it is a nuclear process.
Yes.
However, some quite severe effects are produced in the irradiation or the nuclear burning of these fuels, these atomic fuels, uranium. Now here, for example, is a sample of uranium which has been subjected to irradiation in a nuclear reactor. And we will see as the irradiation continues in this slide, the sample is changing in dimensions, is lengthening, the surface is becoming markedly pitted, and as you can infer from these photographs, the considerable difficulty would be encountered in the utilization of these materials and in the maintenance of dimensions of fuel elements. During the burning or nuclear burning of atomic fuels, a large variety of waste products, both gaseous and solid, are produced as shown in this chart. And in fact, one of the principal problems in reactor materials technology today is learning how to live with, how to accommodate these waste products.
Ben, while you describe where our research is going to take us in the future on these particular topics, I'm going to head back to the office.
In summary, we might say that with respect to the future of reactor materials, there are two major problems. First of all, finding out how to make these fuel elements much more cheaply, much more economically, so that power from atomic energy can be made competitive with power from more conventional sources. Our second problem is learning how to use these fuel elements at higher temperatures and for more prolonged irradiations or burnups.
Thank you, Dr. Lussman, for that very interesting discussion on atomic fuels and the magic metals that we use with them. Not only do we use these exotic materials, but we use also some very ordinary ones. I'd like to show you some of these. For example, this lead pencil that you and I use every day. The lead in it really is graphite.
In a much purified fashion, is used in nuclear reactors to moderate neutrons. Another kind of material is boron. When we work out in the garage and get our hands a little greasy, we often wash with borax. The major component in this that's of interest to the nuclear reactor people is boron, which can be used to absorb neutrons and control a nuclear reaction. In a similar fashion, we can use silver to control these nuclear fires. We will discuss not only these kinds of materials and how they are used, but the design of nuclear reactors in more detail in our future discussions on nuclear energy, the key to tomorrow.
Nuclear Energy, Key to Tomorrow. Produced by WQED for the Educational Television and Radio Center. In cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, atomic fuels. Your host, Dr. Warren Witzik, Manager of Reactor Physics. Special guests, Dr. Benjamin Lustman, Manager of the TWR Metallurgy Subdivision. Technical advisor for the series, Mr. Edward R. Sanford. Engineering supervision by Frank Stuckman and Stephen Zorbas. Production and direction for the series by John W. Ziegler and Robert E. Potts. This is National Educational Television.